episode 34, titled Calculus for ML, Derivatives as Slope, Partial Derivatives, and the Chain Rule, the goal is to see calculus as the steering mechanism that guides models toward lower error rather than as a collection of symbols you must memorize.
DataX questions that touch calculus usually care about your ability to interpret what derivatives mean in optimization and why learning algorithms behave the way they do, not your ability to do longhand differentiation.
When you understand derivatives as slope and gradients as directional guidance, training becomes a story about reducing loss in small, controlled steps. The exam rewards this story because it helps you diagnose issues like unstable training, overshooting, and the impact of regularization, all of which appear in scenario form. Calculus also explains how complex models can still be trained efficiently, because the chain rule lets you compute how changes in one part of a model affect the final error.
This episode will define derivative, partial derivative, gradient, gradient descent, and chain rule in plain language, then connect them to backpropagation and learning rate behavior.
The aim is to make optimization intuition feel natural, so you can answer exam questions about training dynamics with calm confidence. Before we continue, a quick note. This audio course is a companion to the DataX books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series.
A derivative is best understood as slope, meaning it tells you how the output changes when you nudge the input, holding everything else about the function fixed. If you imagine a curve, the slope at a point tells you whether the curve is rising or falling at that location, and how steeply. In modeling, the output you care about is often a loss value, which measures how wrong the model is, and the input you nudge might be a model parameter or a weight. The derivative then tells you how sensitive the loss is to a small change in that parameter, which is exactly the information you need to decide how to adjust it.
If the derivative is positive, increasing the parameter tends to increase the loss locally, and if the derivative is negative, increasing the parameter tends to decrease the loss locally.
The magnitude tells you how strong that effect is, meaning steep slopes imply that small changes have large impact. DataX rewards this interpretation because it lets you reason about why some weights change quickly and others slowly during training, without needing to compute the derivative explicitly.
A partial derivative is the slope with respect to one variable while holding other variables constant, which matters because real models have many parameters influencing the loss at the same time. When you change one weight, you are effectively asking, if everything else stays the same, what happens to the loss when this one weight changes? That everything else stays the same is the conceptual meaning of holding other variables constant, and it keeps the slope interpretation clean. In a multi-parameter setting, you have a partial derivative for each parameter, meaning each weight has its own local slope that tells you how the loss responds to a small change in that weight. This is why training can be viewed as adjusting many knobs at once, each guided by its own slope information. The exam often tests whether you understand that the effect of changing one parameter is measured while others are treated as fixed for that local calculation. Partial derivatives are the reason gradients exist as vectors, because you need a collection of slopes, not just one. DataX rewards this because it shows you understand optimization in the multivariable reality most models live in. A gradient is the collection of partial derivatives, and it can be understood as a direction in parameter space that points toward the steepest increase in the loss. If you picture the loss as a landscape over all possible parameter values, the gradient is like an arrow pointing uphill, showing the direction in which loss increases fastest at the current point. That makes the gradient immediately useful, because if the gradient points uphill, then the negative of the gradient points downhill, which is where you want to go when you are trying to reduce error. The gradient also includes magnitude, which tells you how steep the landscape is, and that influences how large an update might be reasonable. In DataX terms, the gradient is the signal your training algorithm uses to decide how to adjust parameters to reduce loss. The exam rewards gradient intuition because it helps you interpret training instability, slow learning, and sensitivity to learning rate. When you can say that the gradient points towards steepest increase and that you move against it to decrease loss, you have the key idea.
Gradient descent is the method of stepping downhill to reduce loss, using the gradient as your steering guidance.
The core logic is that you compute the gradient at the current parameter setting, then you update parameters in the opposite direction by a small amount, and then you repeat. Each step is intended to reduce the loss, though in messy landscapes there can be bumps, flat regions, and multiple minima, which is why step size and stability matter. The exam typically frames gradient descent as an iterative optimization approach rather than a closed-form solution, and that framing aligns with how many modern models are trained. The important part is that the update is local, meaning it uses slope information at the current point rather than global knowledge of the entire landscape. This is why gradient descent can work even when the loss function is too complex to solve directly, and why it can still fail or struggle when slopes are noisy or when the landscape has challenging geometry.
DataX rewards recognizing gradient descent as controlled repeated downhill stepping because it is the unifying concept behind many training algorithms.
The chain rule is the principle that lets you compute the influence of an input through a sequence of linked computations, which is why it is essential for training layered models.
In plain language, if one quantity affects a second quantity and that second quantity affects a third, then the influence of the first on the third is the product of those influences along the chain.
This matters in machine learning because model outputs are often the result of many nested functions, such as layers in a neural network, where each layer transforms inputs and passes them forward. The chain rule provides a systematic way to compute how a small change in an early weight affects the final loss, even though that weight influences the loss only through many intermediate values.
The exam rewards chain rule understanding because it explains how backpropagation works and why training is possible at scale.
Without the chain rule, you would have no efficient way to assign responsibility for error to individual parameters across layers. When you can say that chain rule passes influence through linked computations, you are describing the core mechanism correctly.
Backpropagation in neural network training is essentially chain rule applied repeatedly across layers to compute gradients efficiently. Each layer produces outputs that feed into the next, and the final loss depends on the last layer's output, so you need to know how each layer's weights contributed to that loss.
Backpropagation computes gradients by moving backward through the network, using local derivatives and the chain rule to propagate error influence to earlier layers. This is why it is called backpropagation, because it propagates information about the loss backward, so that each weight receives an update signal.
The exam often tests this at the intuition level, asking what backpropagation does, and the best answer is that it computes gradients for all weights using the chain rule.
You do not need to write the equations, but you should understand that the method is efficient because it reuses intermediate computations rather than recomputing from scratch. This also ties to stability issues like vanishing or exploding gradients, which are chain rule-related phenomena where repeated multiplication of derivatives can shrink or grow signals. DataX rewards this connection because it shows you understand why the training process behaves the way it does.
Narrating one gradient step helps make the process concrete, and the exam often rewards this kind of operational clarity in performance-based reasoning. You begin at a current set of weights, evaluate the model on data, and compute a loss that measures error. Then you compute the slope information, meaning the gradient, which tells you how loss changes if each weight is nudged. Next, you update each weight slightly in the direction that reduces loss, which is usually the opposite of the gradient direction, scaled by a learning rate. Then you evaluate again and repeat, gradually moving toward a region of lower loss. This narration highlights the key idea that you do not jump directly to the best weights. You walk there step by step, guided by slope information. It also makes clear why the process can be sensitive to step size and why it can take many iterations to converge. DataX rewards this because it shows you understand training as an iterative feedback loop rather than as a single computation. The learning rate is the step size, and it is one of the most important stability controls in gradient descent because it determines how far you move along the update direction each iteration. If the learning rate is too small, training can be painfully slow and can appear stuck, especially in shallow slope regions, because you are taking tiny steps. If the learning rate is too large, training can become unstable because you overshoot the region of lower loss and bounce around or diverge, never settling. The exam may describe a training process where loss oscillates or increases, and the learning rate is a common cause. Learning rate selection is also a trade between speed and stability, which is why schedules and adaptive methods exist, though the exam usually focuses on the conceptual role. A stable learning rate produces gradual, consistent improvement in loss, while an unstable one produces erratic behavior. DataX rewards understanding this because it allows you to choose the correct explanation when a scenario describes unstable learning. Overshooting minima is the intuitive failure mode when you step too large too often, because you keep jumping past the bottom of the loss landscape rather than settling into it. Imagine walking downhill toward the lowest point in a valley, but each step is so large that you leap over the valley floor to the opposite side and then leap back, never finding the bottom. That is what can happen in optimization when the learning rate is too high, or when gradients are steep and you do not scale steps appropriately. The exam may describe loss decreasing briefly and then increasing, or it may describe oscillation around a lower value without convergence, and overshooting is a plausible interpretation. This is not the only cause of instability, but it is one of the most straightforward and common, which is why it appears in learning rate discussions. The correct mitigation in those cases is usually to reduce step size or to use methods that adapt step sizes, not to abandon gradients entirely. DataX rewards this because it reflects practical training intuition. You control the size of updates to maintain stability. Derivatives also connect to regularization penalties, because regularization adds an extra term to the loss that changes the slope and therefore changes the optimization path. Regularization is the idea that you penalize complexity, often by penalizing large weights, which encourages simpler models that generalize better. When you add a penalty term, you change the loss landscape, creating additional slope that pulls weights towards smaller magnitudes. This is why regularization affects training, not only final model complexity, because it changes the gradient at every step. The exam may frame this as, why do regularized models avoid extreme weights? Or, how does regularization influence optimization? And the answer is that the derivative of the penalty contributes to the gradient. This also connects to stability, because regularization can sometimes stabilize training by discouraging very large weights that create steep and unstable gradients. DataX rewards this link because it shows you understand that optimization follows the gradient of the full objective, not just the data fitting term. When you can say that penalties add slope that changes updates, you are reasoning correctly. The most important exam habit here is keeping symbols minimal and focusing on meaning and consequences. because the question is usually about behavior rather than about notation. You should be able to say that a derivative is a sensitivity measure, that a gradient is a collection of sensitivities, that gradient descent is repeated downhill movement guided by those sensitivities, and that the chain rule is how you compute sensitivities through layered computations. You should also be able to connect learning rate to stability, overshooting to two large steps, and regularization to an added force that shapes the path. This level of explanation is technical but not symbolic, and it is exactly what DataX tends to reward. When you stay at this meaning level, you avoid getting trapped in algebra, and you preserve time for interpreting the scenario's real message. This is also how you explain these ideas to colleagues who want to understand training behavior without sitting through a calculus lecture. DataX rewards this because it aligns with professional, instructional communication.
A reliable anchor for this episode is that slope guide's step and chain rule connects layers because it captures the two core ideas you need under pressure. Slope, meaning derivatives and gradients, tells you which direction to move to reduce loss, and that is what makes gradient descent possible. The chain rule tells you how changes in early parameters influence the final loss through multiple linked computations, and that is what makes training deep models feasible. Under exam conditions, this anchor helps you answer what is the role of the derivative and why do we need the chain rule without hesitation. It also keeps you from mixing up forward prediction with backward gradient computation, because you remember that chain rule is about connecting influences across the computation graph. DataX rewards this because it produces consistent, correct interpretation across optimization and neural network questions. When you can recall this anchor, you can stay calm and focused.
To conclude episode 34, explain gradient descent in one sentence, then repeat it slowly, because this is the simplest way to ensure your understanding is clean and exam-ready. To conclude episode 34, explain gradient descent in one sentence, then repeat it slowly, because this is the simplest way to ensure your understanding is clean and exam-ready. A correct one-sentence explanation is that gradient descent repeatedly updates model weights in the direction that reduces loss, using derivatives to choose the downhill direction and a learning rate to control step size. Then, repeat the idea slowly by stating that you compute the gradient of the loss. Step opposite that gradient by a small amount, and repeat until the loss stops improving meaningfully. Add that if the learning rate is too large, you can overshoot and become unstable, and if it is too small, learning becomes slow, because those are common scenario cues. Finally, tie chain rule to backpropagation by stating that the chain rule is how gradients are computed through layered computations, so each weight receives an update signal. If you can narrate that sequence clearly, you will handle DataX questions about derivatives, gradients, and training dynamics with confident, correct judgment. Thanks for listening. For more audio courses, daily newsletters, and more, please visit DailyCyber.News.